Welcome to the Explainer. Today, we're jumping right into what I can honestly only describe as a cinematic journey. We're going to explore the incredible, totally hidden life of seeds. It's absolutely fascinating to uncover how this tiny, armored little vessel, which looks completely inert and quiet, transforms into a massive, complex, living plant. I mean, just think about that for a second. How does a dormant, lifeless-looking pebble awaken to become an entire forest? It's a pretty wild question, right? Because as we'll see today, a seed isn't just a speck of debris. It is a patient protagonist. It's basically a biological survival capsule, embarking on this epic journey, just waiting for the absolute perfect moment to unleash all its potential. Section 1. Inside the Seed Vault, Armor and Payload. Okay, let's dive into this. To really understand this journey, we've got to look at the anatomy. Think of the seed as a highly advanced survival capsule designed by nature. On the outside, we have the seed coat. This protective barrier is formed from a really thick, tough outer layer called the testa and a delicate inner layer called the tegmen. It's literally an armored vault. It acts as a physical barrier against mechanical damage, it keeps out parasites, and, maybe most importantly, it prevents excessive water loss, so the seed doesn't just dry up while it waits. Now, right beneath that armor, we find the endosperm. This is a mass of triploid tissue, which is just a fancy way of saying it's a fascinating genetic anomaly with 3 sets of chromosomes. But functionally, it's the seed's ultimate survival payload. It's packed to the brim with oil, starch, and protein. Because the seed is underground and obviously can't photosynthesize yet, this endosperm is absolutely crucial. It's the packed lunch that nourishes the sleeping embryo until it can reach the sun and feed itself. And right in the center of it all is the embryo, carrying the master blueprint. Think of it like a tiny, dormant, biological factory. It contains all the underdeveloped hardware it needs to build a plant completely from scratch. Up top, you've got the epicotyl, and its tip, the plumule, which are waiting to become the main shoot. Below that is the hypocotyl, kind of acting as a transition zone. Then there's the radicle. That's the embryonic root getting ready to plunge downward. And finally, the cotyledons, which are the embryonic leaves. The whole shebang. Everything the plant needs to get started is packed right into this tiny space. Section 2. Monocots versus dicots, 2 paths of natural design. Now, what's really interesting about this slide is how, as plants evolved, nature actually solved the problem of seed storage in 2 totally distinct ways. First, you have a monocot seed, like corn. This features a single, very thin cotyledon called a scutellum. Because this single leaf is so thin, monocots rely heavily on a massive endosperm to store the bulk of their food. But on the flip side, a dicot seed, like a bean, features 2 distinct, really fleshy cotyledons. In dicots, these 2 seed leaves act as the primary food source themselves, which means the endosperm is often super reduced or even completely absent by the time the seed is fully mature. And when we dive a little deeper into their structures, you'll notice monocots, like maize, actually come with some extra protective gear. They have a sheath called the coleoptile protecting the embryonic shoot, and another called the coleorhiza, protecting the embryonic root. Dicots, like the bean, just don't have these extra sheaths. You can also spot differences in where the plumule is located, and even the basic structure of their seed pods. It's just a fascinating divergence in evolutionary engineering. Section 3. Surviving through seed dormancy. Suspended animation. So a seed doesn't just instantly sprout the second it hits the dirt, right? It actually enters a state of suspended animation. It's a brilliant evolutionary defense mechanism where metabolic activity drops to a bare minimum, allowing the embryo to survive freezing winters, scorching droughts, you name it. And that hard seed coat we talked about, it is a major player in enforcing this dormancy. It imposes severe physical and chemical restraints. A tough coat can literally, mechanically trap the growing plant inside. It can block vital oxygen from getting in, or hold on to chemical inhibitors that stop growth dead in its tracks. To break this kind of dormancy, the seed requires some serious environmental wear and tear, like being battered against rocks, exposed to harsh soil microbes, or even surviving a trip all the way through a bird's digestive tract. But it's not just the hard shell. There's an internal chemical alarm clock at play too, completely driven by plant hormones. The maternal tissue of the plant actually produces a hormone called abscisic acid, or ABA, which basically acts as the brakes. It enforces dormancy and prevents the seed from sprouting prematurely. The seed can only wake up when environmental conditions signal it to produce growth-promoting hormones called gibberellins, or GA. Think of GA as the gas pedal. Once the ratio of the gas pedal completely overpowers the brakes, the alarm clock rings, and the seed finally wakes up. But nature is incredibly cautious. Even if that internal alarm goes off, if the outside world is too stressful, say it's lacking ideal light, water, CO2, or the right temperature, the seed is just going to hit the snooze button and enter what's called secondary dormancy. If you've ever planted seeds in your garden and absolutely nothing sprouted, well, they might have just been playing it safe and waiting for better days. Section 4. The stages of germination, the awakening. So once those perfect conditions are finally met, we reach the grand awakening. This is really the explosive climax of our seed story. Let's move to step 1 and see how this builds. Step 1 is imbibition, which is a rapid, intense absorption of water that swells the seed up. Step 2 is activation, where dormant metabolic enzymes suddenly reawaken. Step 3 is emergence. This is that magical moment where the radicle, the root, physically breaks through the softened seed coat. And finally, step 4 is growth, where the shoot pushes upward to find the sun and the young seedling officially establishes itself. I really want to emphasize a crucial takeaway from the source material here. Water is the absolute master key to this entire process. Imbibition doesn't just physically soften that armored seed coat. The sudden influx of water is the ultimate catalyst that restarts cellular respiration. It activates specific enzymes like amylase, protease, and lipase, which immediately get to work breaking down the starches, proteins, and fat stored in the endosperm and cotyledons. They convert all that stored payload into the immediate usable energy the embryo desperately needs to push its way through the heavy soil. Section 5. Epigeal and hypogeal growth, breaking the surface. And this brilliantly illustrates our final biological act. The seedling has to breach the soil to reach the sunlight, right? Well, this final hurdle requires a choice in strategy. In epigeal germination, dicots like beans play the risk taker. The stem below the seed leaves elongates rapidly, physically pulling the cotyledons right up into the open air above the soil surface, where they turn green and start photosynthesizing. Monocots like maize and peas, however, use hypogeal germination. It's a safer, way more cautious strategy. They leave their cotyledons safely hidden underground, using them purely as a fuel tank, while sending only the delicate shoot up into the open air. To wrap up our explainer today, I just had to share this mind-blowing fact highlighted in the research. Certain seeds can remain dormant for decades until conditions are just right for germination. Decades, literally decades. It is a profound reminder of nature's incredible patience and the sheer, undeniable resilience locked inside that tiny, armored vault we've been uncovering today. So the real takeaway here is that the ground we walk on is absolutely alive with potential. Next time you step outside and walk on the soil, ask yourself, how many dormant forests are waiting right beneath your feet? Their internal clocks just ticking away, waiting for the perfect drop of water to begin their cinematic journey. Thank you so much for joining me on this explainer, and keep exploring.